गुड मॉर्निंग ऑल ऑफ यू। नमस्ते बच्चों, हमेशा खुश रहो बच्चों। माई सेल्फ ओम प्रकाश, फैकल्टी ऑफ डिपार्टमेंट ऑफ मैथमेटिक्स अंडर फैकल्टी ऑफ एजुकेशन एंड methodology. These are the lesson planning. These are the steps for planning a lesson. These are the components of a lesson plan. In today's lecture, I will show you one more example on cyclic group, uh, which correlate with the above previous theorem, which are already taught in your past class. The problem is, let G be a finite group. Let G be a finite group. Let G be a finite group whose order is not divisible by 3. Whose order is not divisible by 3. And suppose A star B to the power 3 equals to A to the power 3 star B to the power 3. For all AB belongs to G. Then saw that G is abelian. Then we have to show that G is abelian. Here, a group, finite group of order which is not divisible by 3. A group is given with finite order which is not divisible by 3, which is not divisible by 3. And suppose here given that a b to the power q equals to aq bq for all ab belongs to G. Then we have to prove that G is an abelian group. For this, let us take a two element a and b belongs to G. Then, as shown in the above, abq equals to aqbq, abq equals to aqbq, and we get abq will be written as ab into ab into ab, which is equals to aqbq, is equals to aqbq. Now, by using cancellation law from left for a and from right for b, we have ba equals to b square because cancellation law holds good in G. Again, we can write ba square equals to a square b square, ba square equals to a square b square. Again, we take baq equals to bqaq, baq equals to bqaq. Then again we can write ba into ba square, ba into ba square equals to bqaq, and again ba into a square b square, because ba square is equal to a square b square in the equation 1. Then we get ba into a square b square is equals to aq bq by using 1. Again, now after multiplying we get b aq b square, baq b square equal to bqaq, and using cancellation law and cancel b, we get aq b square equal to b square aq, aq b square equal to b square aq, aq b square equals to b square aq, aq b square equals to b square aq. Now again, consider a inverse b to the power minus 2 ab square to the power whole cube. Here we can take a inverse as a one element, b inverse as another element, and ab square as a third element. Then we can write a to the power minus 1 to the power 3 for a inverse, and similarly b square we can write b square, b to the power minus 2 we can write b to the power minus 2, and ab square it will be written as ab square to the whole power cube, which is equals to a to the power minus 3 into b to the power minus 2 ab square. That means here we can use simple algebra. which is equals to a to the power minus q b square aq b square, because here b square ab square is nothing but a inverse a b inverse ab b inverse ab, which is a normal form of any element of a group. Then we can write here b square b to the power minus 2 aq b square is equals to b to the power minus q a b square to the power whole q. Don't be confused about this. Then we can write here a to the power q into b square, sorry, b to the power minus 2 b square aq by using associativity, or we can say aq b square equals to b square aq by using equation 2. Then we can write here b to the power minus 2 into b square is equal to e by property of identity element. Again here a to the power q into aq, a to the power minus q into aq is equal to e by using property of identity element. Therefore we can say that order of a inverse b to the power minus 1 ab square divides 3. Order of a to the power minus 1 b to the power minus 2 ab square divides 3. Divides. Therefore we can write here, this implies that order of a inverse b square to the power minus 1 ab square is equals to 1 or 3. 1 or 3. If order of a to the power minus 1 b to the power minus 2 ab square equals to 3, then 3 divides order of g, which is not true. 3 divides order of g, which is not true, because in our questions given the it given that the order of g is not divisible by 3. Therefore order of a inverse b square ab square is equals to 1, which is e. This implies that a inverse b to the power minus 2 ab inverse equals to e. Then we can write ab square equals to b square a by using inverse of property. Now again from 1 we have ab square equals to a square b square, which is equals to a into a b square, which is equals to a into b square a using 3. Therefore we can take b a into b a equals to a b square a b square a, which implies that a b a b equals to a b square, b a b equals to a b square, which is implies that b equals to a b. Hence we can say that for any two element a and b, b equals to a b, or we can say that the group G is an abelian group. The result that we are going to prove now might raise doubt in the mind of the reader as to the validity of the assertion we made easier, and that the converse of Lagrangian theorem does not hold. The converse of the Lagrangian theorem does not hold. But for a cyclic group, the converse of the Lagrangian theorem hold in a finite cyclic group. The converse of the Lagrangian theorem holds in a finite cyclic group, which we have to prove in your next class. This session is powered by the digital version 2.0 JAYOTI VIDYAPEETH Women's University, and I hope all of you are satisfied with my digital session. If you have any query, please mention in the comment box. I will try to solve it. Thank you for watching this lecture video.